Hey, college algebra. This is video number 4 for your fourth problem, fourth example here for section 5-6. Now we're going to be talking about another exponential decay type situation, but with Newton's law of cooling. The GOAT. I think maybe it's up for debate, but you got to put Isaac Newton in the discussion for the GOAT of genius of all time. I mean, how many people take their time off from a pandemic like he did? It was the plague back then. Time off the pandemic, everybody sent home, and he says, I got some spare time. I'm going to invent a branch of calculus, a new system of math. Why not? I mean, come on. That's right up there. So anyway, this guy had his fingers in everything. I mean, look at this. We're talking. He's got a law of cooling. He's got laws of motion. He's got it all. Okay, so anyway, he figured out that this function models the temperature of a substance as it cools. So notice what we got here. We got that function notation going again. This time, T for temperature at a given time equals T subscript 1. This again is going to be the initial temperature of the substance initially at the beginning. I'm not using a subscript 0 because the book used a subscript 0 for something else, and I don't want you to look at the equation in the book and get confused any more than you need to. Okay, so I'm going to stick with what the book says there. T sub 1, maybe that's the first temperature we're looking at, the temperature of the substance initially. Okay, so that's our initial temperature, what it starts at. T sub 1 minus R. I'm using R in a place where the book used T sub 0 because to me that could get really confusing. We're using a subscript 0 for an initial temperature before. I think R makes more sense because we're going to call that the room temperature, what the temperature of the surrounding room is, right? So that's what it's going to cool down to, okay? Cooling down to room temperature. So that is going to be in parentheses together right there. Okay, so that's kind of a multiplier on the base of E again, e to the negative kt, just like we saw with exponential decay. Okay, so we would expect, if you think about this, normal exponential decay is going to go down like this, right? This isn't quite that because it doesn't cool down to 0, like here would be, your 0 baseline, right? It cools down to the room temperature. So there's this plus R. Again, R shows up again because notice that would be a vertical shift, right, of R. So the baseline is going to be the room temperature. So this thing is going to start up here and cool down to the room temperature actually. Starts at some, whatever the T1 is, and cools down to room temperature. That's the baseline right there. Okay, so it's going to look something like that instead of that. So there we go. That's the function. I didn't put it quite in the same order as the book, but hopefully this one makes some sense there. Again, the K is the rate, kind of like the R in our interest problems. So let's look at an example that's like number 19. I think they use a cooling cup of coffee, so I'll do the same thing. Now, their temperature, I think, starts different. I'm going to say my initial temperature is 140 degrees Fahrenheit because I saw one website said that is the ideal coffee temperature. So maybe when I make my morning cup of coffee, I start with a nice, beautiful 140 degree piping hot cup of coffee, and of course, it's instantly going to start cooling down. And it's going to follow this model, this function as it does. Now, just to be a little more consistent with your book, they have it cool down to 0. 0 degrees in a freezer. I'm going to say 5 just for something a little different. Some crazy person comes. Why would you do this? I don't know. But they put this cup of coffee in a freezer. And our temperature probes say our freezers usually run about 5 degrees, we'll say. Okay, so in a freezer with room temperature of 5 degrees. So as I'm kind of gathering information here, my T sub 1 is going to be 140 degrees. My first temperature, so to speak, is that 140 degrees Fahrenheit. My room temperature is going to be a chilly 5 degrees Fahrenheit. Okay. And as we continue on here, after 6 minutes, the temperature has cooled to 70 degrees. So let me look at our function as we progress along. We got the temperature at a given time is T sub 1, which is the 140, minus the room temperature of 5, times e to the negative k T plus the room temperature again, which is 5. That's where we're at so far. Okay. Now, you might wonder what is this for, right? Why do we need this 6 minutes cooled to 70? Because we're just trying to answer the question, what will its temperature be after 12 minutes? Well, a 12-minute time, right? The time is 12 minutes. Why don't I just, isn't that all I need right there? Plug it in. Well, see, the issue is that we have the time right there, 12. Okay, that's fine. But we also have this K number. We don't know the rate of cooling to start with. We don't know how fast it's going to cool off. We're going to have to figure that out. Okay, so that's where this comes in. Because, okay, fine, if you plug 12 in for T, that's great, but you don't have a number to plug in for K. We don't have the K number, all right? So that is what this 6 minutes and cool down to 70 degrees is. Because what that tells me is the final temperature after 6 minutes is 70 degrees. Okay, so now this 6 minutes would be another time number to put in. So here's how this works. This final temperature after, we're going to start with the 6 minutes. The 6 minute time is 70. Okay, and then we're going to put not 12, not yet, but 6 minutes in for the time. 6 minutes. Okay, so it's going to look something like this to start with. 70 equals 140 minus 5. Well, that's 135 times e to the negative k times, okay, now I'm going to put 6 because it's at 6 minutes. 6 minute time is when the temperature is 70. All right, so they had to give us that extra little bit of information, and my plus 5 here, because now we have an equation where the only unknown is the K. And like I said, we're going to have to work out the K. We have to work out the K first before I can finally answer the question using the 12-minute time. So this is a two-step process here. First, we're going to have to use that 6-minute temperature to work out the K, and then I can find the temperature at 12 minutes. So here we go, solving for the K. Right, now we're going to do some algebra. Why not do a good old step-by-step process here? First, we need to subtract that 5. There's that plus 5 at the end. We're going to do that first. Because your freezer temperature is 0, You probably don't have to worry about that step on your homework problem, but I do. Okay, so 65 equals 135 times e to the negative k times 6. I'm going to put the 6 first, like negative 6k, just because we're kind of used to having the variable like that at the end. Okay, so now it's kind of like one of them before, or you've done before hopefully, where we need to divide by the 135 to isolate the e part. Okay, so I'm going to have to divide 65 by 135. I could even reduce that as a fraction, or just use the decimal version there, maybe round it off. Whoops. Change back to red here. We got 0.481, and that repeats, equals e to the negative 6k. Okay, now I've got a few more steps yet to go. Hopefully you're anticipating my next step, and that is cancel out the e with the natural log. So I'm going to do natural log of that number. Natural log of that answer is what? Negative 0.73, and then a whole bunch of decimals after that. And now that's just negative 6k. Okay, I'm just putting a dot because I'm going to let the calculator keep as many decimals as possible until the very end. Now I can divide by the negative 6, because now I got rid of the e, so that's all I got left on the right side. And finally, divide by negative 6. What do we got there? It is about 0.12. I'm going to go 4 decimal places, because that's what you did on the last assignment. That's probably a pretty good amount of precision. 0.1218. So that's a little over 12% per minute. 12 for the k. All right, that's the k. Now, I'm not done with the problem, because it didn't just ask to find the k, it asked for the temperature after 12 minutes. So I haven't answered that question, but I'm in a position where I can now, because now I have all the information I need to plug in 12 minutes as the time, right? So all I got to do from here, I went ahead and made a blank page just in case I needed the room. I don't think I do, because I think at the bottom I can squeeze that in to say the temperature of this coffee after 12 minutes in the freezer, because somebody's playing a cruel joke on me, is going to be, okay, it was 140 minus 5, remember, 135 times e to the negative k, which is 0.1218 approximately, times the time of 12 minutes plus 5-degree room temperature. There we go. And now I can just plug that into the calculator. Let's see what it says. 135 times e to the negative 0.1218 times 12, and then a plus 5. It's telling me it's about 36.3 degrees. Oh, what a tragedy. My coffee has cooled all the way down to close to freezing after 12 minutes in the freezer. Oh boy. Somebody's going to answer for that. Okay, and that should hopefully guide you through that problem. All right. Again, let me know if you have questions, and I'll see you in the next video. Bye-bye.